Hey friends, I'm going to demonstrate and teach you about a Markov chain and a Markov analysis in this tutorial. Before we get started, I will need to tell you some things about a Markov chain and Markov analysis to start with, what those things are. So the first thing that I need to tell you about is what is called the Markov property. And a Markov property is a type of random process, just like any other kind of uh, random probability models. But this model, this property says that for any random process, the only information that you need about the future behavior is the information about the current behavior. Like the past does not influence the future in a Markov property. And so this is a unique kind of probability model. For that reason, it is often called a memoryless model, and it is only dependent on the current state of this events or states, as if you will. So that's what a Markov property is. Now, a Markov chain is a Markov process that has a discrete time, discrete space involved. It's also considered a series of a sequence of states. This is why it's useful in many fields like economics and machine learning, as well as what I'm going to demonstrate here, which is workforce planning. Because a Markov chain is a process, it can be denoted mathematically with a string of values, and those string of values can be used to create a matrix. So you'll hear me say those words a lot, a matrix, because I will need to make one in order to perform an analysis. So once I have created a Markov chain, which is a series of events with with values, then I would be able to perform mathematical functions on them, which is what is called the Markov analysis. So with that, I know that that is a lot, and we're going to go ahead and jump right in and get started. So let me tell you a little bit about the situation that I am in as a internal consultant for an organization. It is my job to forecast the employees for next year, and in future years. That's something that I could use, that I may need to do. So I've decided to use a Markov analysis in order to do this, because part of a workforce planning involves many steps, from a supply analysis, which is the process of analyzing your current employees and the rates of promotion, hiring, turnover, things like that would be a supply analysis. It also involves doing a demand analysis, investigating how many employees makes your organization run, how many more you need to hire in order to keep everything running smoothly. And then there's also something that's called a gap analysis, which is finding the difference in those values, what you have and what you are going to forecast, and where you will be lacking, so that you can implement procedures such as recruitment, hiring, training, and start looking into promotions, if that is and this organization does promote from within. So all of these things, all these moving parts, are very important for an organization to run smoothly. So I think that I can do this using a Markov analysis, because I'm relatively new in my position, so I don't know what was going on in the past, but I know exactly what's going on right now, because let's say I've done these analyses, the supply analyses, and I can get this other information. So I decide that I'm going to use a Markov analysis. And to do that, I'm going to use R. So the first thing that I have done already is install my Markov chain package. This is a great package to use for discrete time Markov chains. A discrete time Markov chain, there are multiple types of Markov chains, but a discrete time Markov chain has a specific, accountable uh, amount of the phases as well as values. So the time that I'm going to be using here is really going to be a year based on performance evaluations that are done yearly. And the states that I'm using, which are both requirements for a Markov chain and a Markov analysis, the states that I am using are for positions within the organization, which are part-time customer service, full-time customer service, supervisor, and manager. Those are the 4 positions that I have, but there's another state that I have, which is exit, because all employees will eventually leave the organization, whether it is through voluntary or involuntary turnover. So people do retire, get fired, for whatever, quit. For whatever reason, there is also this exit state. So those are the discrete states, and there will definitely be the discrete amount of time. So that's why these are called discrete time Markov chains, and that's what this package is for. So I've installed this and I've already libraried the package. I can do that again just to see, to make sure that, it's libraried. I already know it is. So before I even get started, I need to make sure that what I want to do, that the states that an employee can go through, that this even has the Markov property. So, and what I mean by that is that each state is not dependent on, is only dependent on the time right before it, not on any past time, any time in the past. So that means only the state right before the state of the transition. So to do this, I think I've explained that poorly, but I'll re-explain it. To do this, I'm going to look at the job history of employee A. Employee A has been at the organization for 7 years. So I'm going to create a vector that represents the career path of employee A over 7 years. What this represents, this vector, is that the employee A started off as a part-time customer service representative, was promoted to full-time customer service representative, and worked there in that position for 3 more years. In the 5th year, was promoted to a supervisor, stayed in that position for 2 years, and then on the 7th year exited. For whatever reason, I don't need to know why to find out if this is a Markov property. If it is a Markov property, then, for example, this position of supervisor in the 6th year is not related to these positions here for the first 4 years. So a transition position, which is the move from one state to the next, is only dependent on the time right before it. It has no memory. So each of these jumps in years would be considered a transition. So I'm going to go ahead and create this vector. I don't think I explained that really well. So I have my employee A vector here. And I'm going to use this function, verify Markov property, and on the object that I created, employee A, to see if it does indeed follow the Markov property. It does this by using a series of chi-square tests. It basically creates a matrix out of these states and computes the value for that. So I'm going to go ahead and run it. And I do not want to see a significant value for this analysis. So here it's telling me that my chi-square statistic is 0.91, 3 degrees of freedom, and my p-value is not so significant, meaning it is not dependent on the past. It is it's memoryless. So I can go ahead and start doing creating my Markov chain, which is my next step. As a reminder, the Markov chain is the set of values that represents the states, and it can be visualized with the matrix. It's considered to be a matrix. So I'm going to go ahead and create an object called employee MC for Markov chain, and I'm going to use this object to hold the properties of my matrix or my Markov chain. To do this, I'm going to create a new one, with the new function using the Markov chain process, and I needed to define my states vector. So this is a really convenient function that allows me to put all of my arguments into one object. The other way would be to create a multiple vectors and then and then compute them together, string them together. So the states vector are going to be the states that I talked about before, which are the positions that an employee can go through in the organization. So I have in this vector full-time customer service, part-time customer service, supervisor, manager, and exit. So I have 4 positions and 5 states. The next property in my Markov chain is the transition matrix. And it's going to equal a very long vector with some table functions in them. So first is the values vector. And these values I got out of my supply analysis, my hypothetical supply analysis. In reality, they were provided by a textbook. And the resources for that can be found in my paper. And so as you can see, these are just a string of values, and what these represent are probabilities for a matrix of situations, which will make more sense once we print this, and I'll be able to explain what these values mean. I got these, as I said, for my supply analysis, as I investigated the information that I had about my organization this year, and it is the probabilities of employees if they would stay in the same position or transition to a new position, and what those probabilities are for each transition to other positions. These values here are this vector is going to be in a table by row. So, and there would be 5 rows. 5 columns, I'm sorry. Columns, rows, they're the same because it's a matrix. And the name of it is employee chain. So I'll go ahead and create this object, and then I'll print it so we can see what I have created. So I'm just going to run it, and you see here I have created the employee chain, and it tells me the information in the output here says that it's a 5-dimensional discrete Markov chain, and it's defined by the following states, which are the 5 states that I just discussed. The transition matrix is by rows, and that means that these values that I gave, it's going to input them in rows first and then start over, as opposed to entering them in a column form. And then there were 5 values per row or column. So I think I said column up here, but it's 5 values per row. So that was my mistake. It is 5 values per row. And so I'll give you an example of what this means, and we'll start with the full-time customer service representative, which is this row. So from my supply analysis, I found that 40% of full-time customer service representatives that were hired this year, or that started out in this position this year, are still in this position this year. 10% transition to part-time customer service. 10% were promoted to supervisor, and another 40% exited the company. So I that's a high value. It may be normal. I would have to investigate that a little bit more. And then, so Markov chain does have another interesting quality is in that this characteristic of Markov chains is only these rows have to equal 1. And this is different from a contingency table that you may be used to seeing where the rows and the columns must equal 1. In a Markov matrix, a Markov chain, only the rows equal to 1. The values, adding the columns, they are not important. And this can be indicated because of this exit state. And as you can see, exit is zeros all the way across and has a value of 1 at the very end. So if you exited, if you started out as an exit, you have an absolute 100% probability of still being in an exit. And what this it really means is that, I mean, once you leave, you're not coming back, at least not in, you're always in this state. You can't start out from an exit and transition into full-time customer service or part-time customer service, not in the meaning that we're thinking. That's actually called hiring, and that would be a different analysis outside of the scope of this. So I hope that I've explained this transition matrix, and I'll be happy to talk about this at another time. What's exciting about this employee chain, because since this is a Markov chain, now I'm able to perform mathematical functions with this Markov chain. So yay, let's move on. So a couple of quick cool things that you can do in this package is to be able to call specific relationships. So if I had a ton of positions and my supply analysis was really huge and I just wanted to find some probabilities of some transitional probabilities. For example, if I wanted to find out what is the probability that a supervisor will leave this year or next year, or what is the conditional distribution of supervisors, meaning like what is the probability that they will transition to any of those. I can find those with these functions right here, the transitional probability function using the data, the matrix, and the first position or the first state is the state, the from state, and the second state would be the transition to state. So I'm going to run this, and this output tells me that the transition probability from supervisor to exit is this value that is underneath my timer, so I can't even see, but I think it's 0.05, which would make sense because right here in my matrix, supervisor to exit is 0.05, so I'm pretty positive that's what that says. And then there's also the conditional distribution. It works in the same way on the employee, on the Markov chain that I created. And I only want to see the distribution for supervisor. So I can run this line of code and it just recalls the line for supervisors up here, the transition probabilities. So it is a really helpful part of this package. If, like I said, I had a really large matrix and the relationships or the table that it was going to output was much larger than this. So these are just some easy tools. So on to the analysis. So now that I have my Markov chain, I'm ready to look at, begin forecasting the future. So another part of my job is to do a demand analysis, or to know how many employees my organization needs in each position in order to run smoothly and efficiently and be real, and and for performance to be really high. And at this time, our current employees just happen to be the at the most ideal number, which is, and so I'm going to create a vector to represent the demand analysis. I'm going to call it current employees, and I'm just creating the vector here, as you can see. So each space in this vector, like order, is important because this order needs to be in the same position or the same order as my states that are in this vector up here. That's very, very important. So I have 400 full-time customer service, 150 part-time customer service, 75 supervisors, 20 managers, and 0 people exit. That's ideal, right? No exits. So that's my demand analysis, and I'm going to go ahead and run that so that I have that current employees object created, which is my demand analysis. So now when the process of running, performing mathematical processes with these vectors and on the matrix is what is known as a Markov analysis. So the first thing I want to know is what is going to calculate how many employees I will have in each state. This is a forecasting part next year. And I'm creating an object after 1 PE, which means performance evaluation. And I'm going to use the current employees vector that I just created, and I'm going to multiply that times the employee Markov chain. So I'm multiplying a vector times a matrix is what I'm doing here. So I'm going to run it, and I will just print the results. So here we go, and I can't see this because my little timer is over it. I don't know how to move it. So it looks like I have 100. Next year, I can expect to have 193. Oh my gosh, I can't see this number. Full-time customer service, 115 part-time customer service, 111 supervisors, 16 managers, and 208 employees will have exited next year. So that is my first projection for the following year. And so, wow, I've already done a projection using a Markov analysis. Well, I can also use these results to perform my gap analysis, which, like I said, is invaluable to me as an IO psychologist, an organizational planner in this way. Like how many, so of course, I'm just going to do the math. So I'm going to create another object called gap, and I'm going to subtract the object that I made after 1 performance evaluation from the current employee. So it's just another, I'm just creating a difference, which is what a gap is. So I'm going to run this. And then you see here, I'm going to print only 4 columns of this. So I want 1 row and 4 columns. And the reason that I'm doing this is because I cannot have a gap of exiting people. So that value is not important to me how many less I'm going to have. In fact, if you subtract 208 from 0, it's going to be negative 208. So this is the reason that I'm only printing 4 columns. I'm going to go ahead and print that gap analysis, and it shows me right here how many people I will need to hire in each position. This is an estimation because these are based on probabilities, but this tells me that I would be short at least, potentially 206 full-time customer service representatives. I think that says 35. I can't not see this in these numbers. I apologize for that. But look at my supervisor's number. I mean, you could already see here that the supervisor number went up to 111 from 75. So I actually have a surplus of supervisors. So I must be making a lot of promotions. My organization is making a lot of promotions. Um, maybe we're restructuring. There could be a lot of reasons for that, but that's outside the scope of this analysis. And it looks like I'll have 3 managers positions open. And that's good to know because we hire from within, so we promote from within. So potentially I can move one of these supervisors out. Maybe they'll be ready for promotion. There is probably a small probability, no, a full-time. So looky here, my full-time customer service representatives. And my part-time customer service representatives absolutely have zero probability of moving directly into a manager's position. So it looks like I'll have to look at my supervisors to see who I can promote into the manager's position. So this right here has been how you use a Markov analysis to do workforce planning. There's a couple of other things that I can do and that I'm going to do really quickly, only because I mentioned them in my paper. And so I can also forecast how many employees would be I'll have left from this year is what I'm saying, after 2 years and after 5 years. And it's the same math. I'm using the current employees vector that I created up here. And after 2 years, right, it's just the employee matrix, my Markov chain times itself because it's after 2 employee performance evaluations. And I'm just, multiplying this to create the estimation for after 2 years. And I can do the same thing for after 5 performance evaluations or after 5 years. And as you can see here, I've just used the caret for this mathematical expression instead to indicate that the employee matrix should be multiplied by the 5th power. So I'm just going to create these and run them. And these also have some pretty significant results. So after 2 years, you see I still have more supervisors, but in my 5th year, I start losing those supervisors again. I've had almost 500 people exit the company in 5 years. I can't see behind my timer right here, but I think this, if I remember correctly, this number is really low for full-time customer service. And even part-time customer service, but full-time customer service is most stark. It has the most employees that turn over each year, and definitely it's very stark for the 5th year. So even though these projections may go out for 2 and 5 years, it is only an estimation because I'm using this year's value. So it's just, oh, I don't know what I've done here. I'm going to close that. Sorry, it's in the way. So it's just an estimation in a way to see what these future discrete states would look like and during these discrete time periods. And the last thing that I'm going to do is make a pretty visual. So I'm just going to plot my Markov chain using the plot function. This program, this package that I'm using actually uses, it loads the iGraph package. So these are somewhat familiar, but it creates a visual representation of the Markov chain or the flow of the probabilities and the directional probabilities, to be specific, of each state to every other state. So, so one of the things that I can notice from this is that all of the states go to exit, and here you have the directional value. So some, like part-time and full-time customer service, there's a probability going back and forth between them, but you see here from where's one? From supervisor to manager. Most managers don't go back to supervisors. Um, So, and then there's the loop because there is a probability that in the next transition or in the next discrete time period that an employee will stay in the same position. So that is also a probability. So I have discussed the Markov process, Markov chains, and Markov analyses. And an advantage in using this is that it is an excellent tool to be able to forecast uh, an organization's needs for workforce planning. So this is a really good tool for an IO psychologist or an internal consultant to use. What's important to note is that these are mathematical projections, they're probabilities, they have no explanatory power to them whatsoever. This analysis in no way can tell you why of anything. It can only give you information or about what is happening. And so you would definitely, if the turnover was of interest or why there were so many supervisors, in the following year, if there would need to be some type of follow-up analyses done, or interventions, climate surveys, focus groups to get to the answer as to why these things are going on in the organization. So thanks for listening. Now you know all about Markov analysis.